Yeah, it's a process introduced.
Oh, moment, let me.
Her talk is Topological approach to algebraic genus to singular fibers. Please.
Okay, thank you very much for the invitation and the introduction and for organizing this session. It's a great pleasure giving a talk here. So I will talk about my recent joint works with Jeremy Van Horn Morris from the University of Arkansas. And we worked on genus to singular fibrations, and then we analyzed their topology. So I will start with some basic information. These are well known, but I thought if you are not in the field, maybe I should introduce the basics that I will keep using them during my talk. So a symplectic manifold, what are those? These are smooth manifolds coming with some special differential two forms. These are closed non-degenerate differential two forms. So these are a special class inside the smooth manifolds with that additional extra geometric structure. And these are all even dimensional and orientable manifolds. And my research is mostly in dimension 4. I'm interested in 4 manifolds. And we have those big results by Donaldson and Gompf. They showed that there is a basically one-to-one correspondence between symplectic 4 manifolds and the Lefschetz pencils. And I will describe what these are. But basically, Lefschetz pencils are giving us more concrete way of understanding and studying symplectic 4 manifolds. And the pencils, when we say pencils of curves, these are collections of curves. And in the pencil, we have some base points. Every member of the pencil must pass through those base points. And when we do blow-ups at those base points, we get a fibration structure. And the blown-up points becomes your sections of the fibration. And then we call them Lefschetz fibrations. And this is the formal definition. Basically, when we say a Lefschetz fibration, it is a surjection from a 4-dimensional manifold onto a 2-dimensional manifold. And we allow this map to have singularities, but they should be only of this type, this specific type. And or if you do coordinate change, instead of z1 squared plus z2 squared, you may make it z1 times z2. But basically, this is telling you that all singularities will be of like nodal type singularities. We call them Lefschetz type singularities. And here we are working in orientation preserving complex coordinates. And each singular fiber, as I just said, is a nodal singularity. And how do we obtain them? We obtain such singularities by collapsing a simple closed curve in a nearby smooth fiber. And we call them the vanishing cycles of the fibration. And the monodrome around a singular fiber is given by a positive daintivist. Positive means right-handed daintivist along the vanishing cycle. So these are basically self-diffeomorphisms on your smooth or generic fiber. And an ordered list of right-handed daintivists in the mapping class group is called a positive factorization. And these positive factorizations determine the Lefschetz fibrations over the 2-disk D2. And in here, I'm talking about mapping class groups. In the morning, Roberta mentioned mapping class groups in terms of homeomorphisms, but here we are considering them in terms of diffeomorphisms. So this is the group of isotopic class of orientation preserving self-diffeomorphisms of the smooth fiber. And in our case, these are our generic or smooth fibers. These are genus G surfaces with K boundary components. And mapping class groups are one of the main tools when we study Lefschetz fibrations. And as I just said, when you have a positive factorization, when you compute that and know that, then it completely determines your fibration over the 2-disk. It tells you what is your total space, what is the corresponding 4 manifold. So it gives us a lot of information. So these are all background. And now I will give some history related to our work. I will start with genus 1 fibrations. So there are well-known papers by Kodaira, and Kodaira classified all singular fibers in pencils of elliptic curves. So elliptic curves again means that these are just torus, 2 torus, or tori. And he showed that in such a pencil, in a collection of such elliptic curves passing through certain base points, each fiber is either an elliptic curve, torus, or a rational curve, which is two-sphere. So we have complex structures here. That is why we work with curves. a rational curve with a node or cusp on that, or you can also have certain sums of spheres of self-intersections -2. So this is the complete list given by Kodaira. So if you have a fibration over 2 disk, genus 1 fibration, so the smooth fibers are just tori, and he gives us all possible singular fibers that you can have. And this is the complete list. So we have configurations of spheres. These are all these lines are representing spheres, and there are multiplicities also. But for us, self-intersections are much more important. Or you may have a nodal type singularity, like this one here. It is Lefschetz type singularity. Or you can have a cusp also. And he showed that this is the complete list in genus 1 fibrations over 2 disk. And then later, Herrer, Kass, and Kirby gave the monodromy factorizations of Kodaira fibrations. And by using these factorizations, in the literature, we have a lot of exotic four-manifold constructions. When I say exotic, we mean that these are, homeomorphic four-manifolds. These are homeomorphic to each other, topologically the same, but they are not diffeomorphic to each other. So their smooth structures are different. And this is my main research team. We are interested in constructing exotic four-manifolds related to big open problems in the area. And by using the work of Herrer, Kass, and Kirby, so many people constructed exotic four-manifolds. And basically, when you start the monodromy factorizations on your manifolds, out of that algebraic information, you can pass to geometry, basically. You can obtain the configurations of curves by just looking at those factorizations. You are able to draw your configurations. And then you use those configurations in your surgeries, either smooth or symplectic surgeries. We call them cut and paste operations to obtain small exotic four-manifolds. Or if you have your global monodromy factorization for your total space for the closed four-manifold, then in that word, it is an algebraic information again, you can do monodromy substitutions. There are results for certain specific substitutions. People show that they correspond to, rational blowdowns or such other surgeries. And by using just algebraic substitutions, we can again obtain exotic four-manifolds. And our theorem with Jeremy Van Horn Morris establishes this dictionary in genus 2 case. So, all these previous works were about genus 1 fibrations. Now we studied genus 2 fibrations, and we give one-to-one correspondence between the genus 2 singular fibers and also their monodromy factorizations. And I will give details of this work, basically. Let me start with now genus 2 fibrations. Namikawa Ueno, after Kodaira, about 10 years later, they gave the classification of all singularities in genus 2 fibrations, and they showed that there are in total 120 types. Let me show you Kodaira's work again. So Kodaira did this work in '63, and this was his list. The list is a lot shorter in genus 1 case. These are all, of course, possibilities. You don't have much room to create more interesting things. But in genus 2 case, we have so much more types of singular fibers, and they gave the whole list in their paper. And these singularities are now configurations of spheres and tori. So now the additional part is in some of your singular fibers, instead of spheres, you may have torus components. And again, we have self-intersections and multiplicities for each of those components. And let me be a bit more precise here. So let's say you have some map. It is a complex algebraic family of curves, basically. In your X, you have such a family of curves of genus 2 over some disk, small disk in C. And your X, the total space, is a minimal non-singular complex analytic surface. And the pi, the map, is smooth over the punctured disk. Away from origin, it is just smooth, so you have a fiber bundle, basically. For every point that you take on your punctured disk, the fiber upstairs is a compact non-singular curve, which is a Riemann surface of genus 2. And the restriction of your map to that punctured disk is just a smooth fiber bundle. But only over the origin, we have the singularity. and we call it central fiber, which is over the origin, the preimage of 0 under pi, and it is a singular complex algebraic curve. And our goal was understanding these singular objects. What are those, and how can we understand their topology? And then we use them to construct exotic form manifolds, basically. And such families of curves happening in your total space, these are called degenerating families of algebraic curves. The idea is very similar to what is happening in the Lefschetz vibrations. Here it is a bit more general, and in the base you take some point in your puncture disk, and from this point you are approaching to the origin. As you approach to the origin, upstairs, your smooth fiber, Genus 2 Riemann surface, degenerates into some singular fiber. So therefore we call them degenerating families of algebraic curves, but these are a bit more general than Lefschetz vibrations, because in the Lefschetz vibrations we allow only nodal type singularities. But here the singularities are much more complicated. They are not necessarily only nodal type. We can have much worse singularities. We call them compound singularities, maybe cuspidal type or higher order cusps and more complicated things. And then we have, I will give a couple more terminology here. We have atomic singular fibers. These are defined as the singular fibers that you cannot split them by any perturbation of the degenerating families into fibrations with multiple simpler singular fibers. So when we say atomic, they are in the simplest possible type. You cannot split them into anything simpler. So nodal type, Lefschetz type singularities are atomic in this sense. And Shaw and Miles-Reid proposed this problem. Can you determine all the atomic singular fibers in any genus G vibration? And then in the genus 2 case, it was studied by many people. Here is some list, but it may not be complete. Shaw, Horikawa, and Person, then Arakawa and Ashikaga studied this problem from the algebraic geometry sense. And then from the topological perspective, Matsumoto and Montesinos also studied this problem, and also Ishizaka. And Namikawa Ueno's list of fibers, I said these are 120 types. They are given in 4 groups. And only in the first group of those fibers, the first group consists of fibers with finite order monodromies. This happens only in the first group of the paper, and they have finite order monodromies. In the others, they have infinite orders. And in this sense, this first group of fibers are analogous to Kodaira's fibers. So these are the most interesting and useful ones for us, and that is why we studied this first group in our paper. And this first group received some attention in the literature, again by Matsumoto and Ishizaka, and then later by Gonglu and Tan, and also Ahmedov and myself, Anar Ahmedov and myself, we studied this first group of fibers. So in that work with my PhD advisor, we work with closed form manifolds that are the total spaces of algebraic fibrations over the 2 sphere. They had only 2 singular fibers. And then we work with 2 such pairs of fibrations, 2 different fibrations. By using them, we constructed small exotic form manifolds. Exotic CP2 complex projective plane blown up at 6 points and 7 points. And also we had bigger manifolds, 3 CP2 blown up at 16 points, and 17, 18, and 19 points to be precise. But this is my previous work. And now I will briefly talk about more recent work. This is joined with, again, Jeremy. And this is singular fibers in algebraic fibrations of genus 2 and their monodromy factorizations. I will just, I don't have too much time, but I will give the main idea of this work. So decomposing singularities into their atomic pieces, or basically this means that you are deforming the singular fibration into a Lefschetz fibration. And it is called morphification by Miles-Reid. And in our work, we first construct the Namikawa-Ueno fibers in the first group, having finite order monodromies. And then for those, we give explicit morphifications of them. We deform all of them into Lefschetz fibrations to be able to talk about symplectic form manifolds. And then we give the daintiest factorizations of each of those fibers and fibrations. And our result can be thought as like analogous to Harrer, Kass, and Kirby's results on Kodaira singular fibers. But again, we are on genus 2 case here, and our method is also completely different than their method. Here we use contact and symplectic topology, and the tools are proofs, our approach is completely different than Harrer, Kass, and Kirby. And so there are different aspects of our work. Algebraically, we first resolve those singularities given by polynomials. We resolve them, and then we reconstruct the Namikawa-Ueno fibers. In short, I just call it NU fibers. And holomorphically, we do complex deformations of the singular fibrations into Lefschetz fibrations. And we do that in a careful way to be able to give explicit daintiest factorizations. And due to such care, these deformations are actually deformations of the underlying complex vibration on the resolution space. We resolve the singularity and we look at the resolution space, and we are actually giving complex deformation of those. And these deformations give the compositions of the singularities into their atomic pieces. So we obtain nodal type singularities out of one complex compound singularity. We perturb that in a careful way so that out of one complex singularity we have simpler types atomic pieces. And then symplectically we find the monodromy factorizations of these resulting Lefschetz fibrations. So this is some brief summary here. And moreover, our theorem is giving both a characterization of the symplectic fibrations that underlie these algebraic families, and also the symplectic structures of the underlying algebraic surfaces, which we access them via the Plumbing diagrams that we construct in the resolutions of singularities. When we resolve the singularity, it gives us configurations of curves, as I just showed some pictures, and we call them Plumbing diagrams. And that is what I'm saying here. And then we cover all the fibers of Namikawa-Ueno with finite order monodromies in the first group of their list. And then we further generalize their list and we look at some additional fibrations. And so we give a dictionary between the symplectic curve configurations coming from our resolution process, the resolution graphs of the singularities, and their monodromy factorizations. We do that for all singularities of such genus 2 fibrations. And our methods and these discovered correspondences between curve configurations and monodromy factorizations, you can apply them to any arbitrary Lefschetz fibrations and pencils. So our method is a general approach, and it works for any type of Lefschetz fibrations and pencils. Even at the beginning, it doesn't have to be Lefschetz. You can start with any type of singularity, and by using our method, you can perturb them, deform them into Lefschetz fibrations, and then again, by using our methods, you can compute their monodromy factorizations. So let me give a bit more details about our work. So we are working with polynomials in C3, x, y, and t are complex coordinates, and by v of f, I denote these zero sets of these polynomials. So these are algebraic varieties. And each of these algebraic varieties, Vf, has a fibration by algebraic curves with only one singular fiber. And we call them compound singularities, as I just said. These are more complicated than a Lefschetz singularity. And the generic fibers, generic means smooth fibers, they are not singular. The generic fibers of such fibrations are either genus 2 surfaces with one boundary component or genus 2 surfaces with two boundary components. And in general, this algebraic variety is a singular variety that we resolve, and then we call the resolution space XF. And then this the fibration on VF, originally having some complicated singularity, that fibration lifts to the fibration to the resolution space XF, and the singular fiber lifts to its resolution graph. So that resolution graph is the configurations of spheres and tori, and they are the interesting objects for us to be able to do cut and paste operations. And this is our first theorem. So let's say f is one of those following polynomials. So the power of t's are changing. In the first family case from 1 up to 10 and so on. And then we look at the zero sets of those polynomials. These are singular algebraic varieties, as I just said. And then we look at the resolutions of those. So this resolution space admits, we showed that it admits an algebraic fibration by hyperelliptic curves, where all the curves are smooth except when t is equal to 0. So over the origin, t is the fibration direction. Over the origin, again, we have a singularity, and everywhere else we have smooth fibrations. And the central fiber over this origin, we construct all of these central fibers. I will show you some pictures, but we construct all of them in our work. And then from those, we also construct the Namikawa-Ueno fibers. So there are tons of pictures. I will quickly go over, show them, just to show them, but these are on archive, so you can take a look if you are interested in. But one by one, we do all resolutions. The resolution is coming from Nemetzy's algorithm, and it is telling us how to resolve the singularities. You just do step by step, and at the end, you construct the desired types of fibers given by Namikawa-Ueno. And we have tons of pictures, so I cannot talk about all of them, but we obtain the exact same types. And then, after constructing those central fibers, next we split these fibrations on the resolution spaces into Lefschetz fibrations. And we also give their monodromies. This is our second result. So the setup is as before. And for each of these ones, we know what is the central fiber, what kind of configuration we have. And for that configuration, we figure out its corresponding monodrom factorization. We have a one-to-one correspondence here. For each value of k, we have the central fiber, and then for that fibration, we give specific explicit monodrom factorization of that fibration. So between this list from 1 up to 4, and between these factorizations in the mapping class group, we have a one-to-one correspondence. So yeah, as I just said, we split these fibrations into Lefschetz type, and then we compute their positive monodrom factorizations. And the generic fibers here are either Genus 2 surfaces with one boundary or two boundary components. And we give all of these words in a specific way. Again, I can show you whole list, but it may not be that helpful, so I will maybe skip this part. I have 5 minutes. So these are all in the paper, but all of these words are corresponding to such positive factorizations, and here each tau is the dativist corresponding to the dativist around the corresponding vanishing cycle in the fiber.
You have almost 2 minutes. We need to keep some time for question discussion.
Okay, then let me hurry up. So these are the pictures for the generic fibers, basically. So here we have one boundary component, and here we have two boundary components. And when we say tau 1, for instance, this is the dativist along this vanishing cycle, and so on. So these are the simpler types. And then we have some more complicated curves in the list. We also specifically show how to obtain them, how to prove them. And moreover, the monodrom factorizations in our list, they have the right orders as their resolution graphs. So in our first theorem, when we resolve and we obtain central fibers, we had these orders in these 4 families. And the orders are matching up nicely here as expected. The monodromies are also having the same orders. And now this is our second paper. Quickly, I will just talk about this. Again, this is joined with Jeremy. And the main difference is in our first work, we constructed all Genus 2 fibers that have finite order monodromies. We call them periodic monodromies. And we built them in a different way than given by Namikawa-Ueno, but we constructed them from the same polynomials given by them. However, not all the singularities in the list of Namikawa-Ueno are of the same type, and we cannot obtain them, we cannot resolve them by using the same methods. So some different approach is needed. Then in our more recent work, we have worked on these singularities, those different types of singularities, and we constructed them from different polynomials. So we figured out what is the correct polynomial which would give us that configuration, and then we constructed them from completely different polynomials. And we again obtained the exact same fibers as they give on their list. Here I say suggested by Namikawa Ueno because they don't show us how to obtain them. The paper is very long, but they do a couple cases in the paper. Of course, they cannot do 120 types. So for those types, there is no proof in their paper. They just say that this is the polynomial for this configuration, but that polynomial doesn't give us the desired configuration. So we have found different polynomials and we obtained those fibers. And when I say the exact same type, here is what I mean. For each singularity, we obtain the same configuration as given by them, and all the other information, the multiplicities, self-intersections of each irreducible components, also agree with their fibers. And then we deformed these singularities into Lefschetz fibrations again and found modular factorizations. Moreover, we also constructed exotic four manifolds in this second paper. We constructed exotic 3 CP2 blown up at 13 points. Yeah, and in different ways. And this is our statement. In the second paper, we worked on this family, and then we computed all factorizations. And by using some of them, we constructed exotic four manifolds. And sorry about that, but I will stop here. Thank you very much.
Thank you, and I will stop the recording now. Thank you very much for your very interesting talk.
Thank you for